In this video, we are going to learn how to establish trigonometric identities. Now, this is part 2 of a 2-part video lesson, so if you haven't watched part 1 yet, please go back and watch part 1 before you watch part 2. Now, we're going to continue to establish these identities. This expression on the left can incidentally be simplified to 2 cosecant of theta. Now, I'm going to keep my end goal in mind here. This is just one term, while this is 2 terms. So I'm going to find a way to combine these 2 fractions into one. And the best way I know how to do that is to find a common denominator. So I'm going to take sine of theta over 1 plus cosine of theta, and I multiply the numerator and the denominator by sine of theta. While I'll take 1 plus cosine theta over sine theta, and I'll multiply its numerator and denominator by the other fraction's denominator, 1 plus cosine of theta. So my new common denominator is just going to be 1 plus cosine of theta times sine theta, and my numerator is going to be a bit more involved. So I will have a pretty large numerator, but all over 1 plus cosine of theta times sine of theta. So up top I have sine times sine, so that'll be sine squared of theta, plus 1 plus cosine of theta times 1 plus cosine of theta, which I have to multiply these 2 binomials out by distributing. So I'll have 1 plus cosine of theta times 1, so that's 1 plus cosine of theta, and 1 plus cosine of theta times cosine of theta, which is another cosine of theta, plus cosine squared of theta. So now combining like terms and rearranging my terms just a little bit, I can get 2 cosine of theta plus sine squared of theta plus cosine squared of theta plus 1 all over 1 plus cosine of theta times sine of theta. Now before I give up hope, again, I know cosecant of theta is 1 over sine. So the fact that sine is my denominator right now with this one big fraction means I need to focus on maybe getting this by itself in my denominator, which means I need a 1 plus cosine in my numerator, which I don't quite have yet because I have these sine squared and cosine squareds. But luckily, these 2 terms can actually come together to give me 1, and that is the Pythagorean identity. Known as sine squared of theta plus cosine squared of theta is equal to 1. So now I can rewrite my numerator as 2 cosine of theta, and that's now 1 plus 1, so now I have plus 2, all over 1 plus cosine of theta times sine. And again, luckily, if I can factor out a 2 in my numerator, and I'll be left with cosine of theta plus 1. And so again, all will be over 1 plus cosine of theta times sine of theta. And that term I wanted to cancel out, so I could be left with cosecant, can now be canceled out. And I'm left with 2 over sine of theta, which luckily, due to the reciprocal identity, I can rewrite as cosecant of theta. So I'll end up with 2 cosecant of theta. Again, these usually do take some time, so take your time through it, but always keep that end goal in mind. I knew this was one term, so I knew I had to find a common denominator in order to solve this. Now next up, I have tangent v plus cotangent v over secant v times cosecant v. Now again, I have lots of different trig functions here. So another great strategy is to convert everything into sines and cosines. So I know that tangent of v is sine of v over cosine of v. Cotangent of v is cosine of v over sine of v all over 1 over cosine v times 1 over sine v. And that numerator right here, just like over here, has two different terms. Well, my answer only has one term, so I should probably combine my numerator into one fraction. So maybe I can find a pattern there. So if I multiply the top and the bottom of this less fraction by sine of v, I'll be left with sine squared of v plus cosine on top and bottom of the other fraction, cosine squared of v, all over cosine of v times sine of v. That's the common denominator once I multiply that out. And this is all over 1 over cosine of v times sine of v. And now that numerator, sine squared of v plus cosine squared of v, can be simplified down to 1. So now I have 1 over cosine v times sine of v. That's the numerator. And then I'm dividing by this fraction in the denominator, so I can multiply by the reciprocal of the denominator, which is cosine of v sine of v over 1. You'll see here that the cosine v and the sine of v cancel out, and this will leave me with just 1. So this complicated expression is just 1, and I've now proved why it is 1. Now lastly, I have 1 minus cosine of theta over cosine is equal to cosine of theta over sine. So now we're using a technique called conjugates in order to solve this one. So I can take 1 minus sine of theta over cosine theta. The reason why I want to use a conjugate here is because this will create a difference of squares, which will lead me to be able to use my Pythagorean identity in my numerator, which will help me get to that cosine up there that I'm seeing. But whatever you do to the top, you must also do to the bottom. And what's really nice is now I have 1 plus cosine in my denominator, like I want in my ending. So hopefully I'll be able just to cancel out that cosine later. So you see here I'm planning ahead. The top is conjugates, so I can use that Pythagorean identity to be able to change sine squared into a cosine squared. And down here I'm thinking ahead by multiplying by 1 plus cosine of theta, so that I have a 1 plus sine theta, so I have 1 next to that cosine theta. So then maybe I can cancel out this cosine theta later. So lots of foresight went into that decision there. So when I multiply this out, these are difference of squares. So I end up with 1 squared, which is 1, minus sine squared of theta, all over cosine of theta times 1 plus sine theta. And I'm not distributing that because I want that 1 plus sine theta in my denominator. Now, thinking about my Pythagorean identity, sine squared theta plus cosine squared theta equals 1. If I were to subtract sine squared theta, I would get 1 minus sine squared theta on the right. And now I see that 1 minus sine squared theta can be replaced with cosine squared of theta, all over cosine of theta times 1 plus sine theta. And very conveniently, I have two cosine factors in my numerator and 1 in my denominator. So 1 can be canceled out of both the numerator and denominator, leaving me with cosine of theta over 1 plus sine of theta, which is what I was going for. Now it's a more tricky identity to establish. But now, generally when you are establishing identities, there are like 4 things definitely keep in mind. One is almost always preferable to start with the side containing the more complicated expression. Sometimes they'll look equally complicated, so you can start on either side, but in the cases like you see here on the left side of the equation looked way more complicated, so start on that side. But if the right side ever looks more complicated, you can always start there and work your way to the left side of the equation. Now, if you ever have sums or differences of quotients, like we saw here in the top left, finding a common denominator is the best way to get them down to a single quotient. We did it over here as well with tangent and cotangent eventually. And sometimes rewriting one side in terms of sine and cosine only will help. If you put in the sine and cosine only, it will usually help. You saw me use it over here, where I made everything sines and cosines, and that just helped me cancel out more things to get to my answer. And lastly, always keep your goal in mind. As you manipulate one side of the expression, you must keep in mind what form the other side of the expression, the other side of the equation is. So that's helped me here think about, okay, I have a sign in my denominator now, so I'm on a good pathway to eventually only be left with sign in my denominator, which led to that answer. So keeping that goal in mind is a great way to establish identities. And that is how you establish trigonometric identities.